So obviously, there are certain basic connectivity services that are required in cloud computing, and this is necessary to be able to stitch together virtualized infrastructure. A newly created or resumed virtual machine must be on the network, must be accessible from the network, obviously. And cloud control frameworks have various ways to manage this connectivity, and generally, or often, ad hoc ways to create this connectivity so that newly created virtual machines can be accessed. In general, the way that that's done for the most part is by the creation of virtual LANs or VLANs. VLANs are implemented via the insertion of a tag in each packet. There's a IEEE standard that describes the way that these tags appear, and so it's relatively straightforward to create a virtual interface or a virtual network via this tagging mechanism, and this can be accomplished, the tagging can be accomplished in virtual switches or physical switches, network devices, in the host, in various ways. So this is relatively straightforward. And there are other virtual network technologies such as MPLS, they're really beyond the scope of today, that can be used. Essentially, they all are function by the creation of or insertion of tags and specialized handling of the packets on the network on the basis of those tags. So later today, you'll be hearing a bit about OpenStack, which is a control framework for creation of and management of virtual infrastructure, virtual machines. And Quantum is a component of OpenStack, which is designed to address the network connectivity, to make network connectivity an explicit part of the framework rather than the sort of implicit way in which it's handled in general. In Quantum, the user, through an API, through a network interface, has the ability to create virtual networks, create ports, and attach to those ports and the networks inside a cloud provider's infrastructure. So whether it's via virtual switches, software switches, or hardware switches, or some combination of the two, Quantum provides an API to allow VMs to be stitched together in a way that is specified by the user, by the client. A related idea to Quantum is the notion of dynamic circuit networks. So dynamic circuit networks implement what is referred to often as bandwidth on demand. So they are on-demand, point-to-point circuits, generally across wide area networks. They're created varying from a lifetime of a few hours to a few days, and they're really designed in response to bandwidth-intensive applications and projects and virtual organizations that require deterministic network connectivity, that have high data movement demands, and thus justify the explicit creation of virtual networks, virtual links to be used. So relatively short periods of time, in some cases, longer periods of time, as I said, in other cases. For instance, experiments using the LHC in Switzerland have made use of dynamic circuit networks and also dedicated networks to stream the data to a number of constituents with deterministic performance and achieving the data movement requirements that they identified in terms of getting this huge volume of data around the world in a timely fashion. Other projects, telemedicine, radio astronomy, have taken advantage of dynamic circuit networks as well. This technology is still in active development. So these are deployed today in networks like Internet 2 and the Department of Energy's ESNet network, the GÉANT network in Europe that connects the various countries in Europe, others in the Asia Pacific region, in South America, and are deploying these, and there is an active community developing standards to stitch these together such that international collaborations can allocate virtual circuits across around the world. And this is an area so they're deployed, but it's moving quickly, and there's an active standardization effort in the Open Grid Forum, and then the GLIF organization working together to create this and provide this and extend the functionality of this capability. So thinking about virtualization of networks as an aside for a moment is important. I believe that networks will follow the trends that led processors to the multi-core revolution, in a sense. In processors for multi-core, for quite some time, we heard that the processors would reach the end of frequency scaling, that they would no longer be able to just make a single faster processor. And we heard that for many years. Eventually it turned out to be true. And now we have the multi-core revolution, which means there are many more processing elements operating at slower speed, working together. And essentially the hardware designers, for concerns of power and the continuing ability to scale up more transistors, said, let's push this back to the application. So rather than 10 years ago, if an application didn't meet the performance requirements, one solution to performance was just to wait until the next revision of the processor came out that was 10%, 20% faster, and the performance improved commensurately. Multi-core revolution meant that really, rather than just riding frequency scaling, performance was pushed back to the software. So now there are many more processing elements, and the software folks, you need to figure out what to do with that. So networks continue to scale up in terms of frequency, but I believe that they're scaling up more slowly nowadays, and I believe that we will see a time in the future when single link speeds will not become any faster, but bundles of parallel links will be the norm. And in fact, this is already happening in a sense with technologies like dense wave division multiplexing, which allow multiplexing based on wavelengths or based on bands, based on colors of light, essentially. So rather than scaling up to 100 gigabit link, it's far easier to have 10 gigabit links running in parallel. So very much like multi-core processors, that means that the ability to use those parallel links, those parallel networks, is now back to the software, back to the users. So a solution to this, one way that we can take advantage of these is with dynamic networks. The ability to create a virtual network on demand means that we don't have to worry about keeping everything together in one large pipe. We can separate pipes, we can dynamically create high occupancy HOV lanes for things that really need to move fast. And that is a challenge, but it's also an opportunity in terms of cloud computing, especially in that this virtualization meshes very well with the idea that we'll just create virtual infrastructure from distributed resources on demand. So if applications infrastructure can allocate links on demand, then this solves the problem partially. And I believe that's a direct analogy.